probability, inference, uncertain inference, and together at the same time to give you an idea of a way to geometrize this problem in the frame of twistor theory by Professor Roger Penrose. Now I have two groups together. One purely inference theme work, and second the geometrical side. And for this reason, you have two introductions. First introduction about uncertain inference, and second introduction about the idea of twistor theory. And then some record on the quantum reality, and then I will try to explain you what the holistic nature of the general physical found by Roger Penrose consists of, and then I will end with probabilities and holicity, uncertainty, and probability. Now, as you know, there are at least two theories of probability, classical and quantum theory. And for classical, two theories also, subjective and objective probability. This question of the difference of between subjective and objective probability propagates in quantum mechanics. And what is very important for this talk is that quantum mechanics gives probabilities a physical meaning, and I propose to try to carry off a geometrization of this physical meaning by means of the twistor theory. You know Ronald Heinler Fischer, and it is in his talk about historical talk about inference in probability, and very interesting talk from the point of view of probability and from the historical point of view of mathematics. The steps, some hesitating, some even fast, but which may have come. I'm not like.
They're not fortunate.
Yeah. Mm-hmm. It may be, and how in particular, it may be applied to observational facts with their limitation, the paucity in number, and the imperfect precision, and yet draw from them precisely knows those inferences which the observation warrant. The idea of probability seems to have been an essentially new one in mathematical thought. It was a concept sui generis, rather like the notion of temperature in physics, and it was particularly novel, Fischer says, in this, that it brought uncertain consequences within the domain of exact or rigorous thought. From this point in time, there are no excuses for mathematicians to confuse rigor with certainty. In the discussion on probability, the uncertainty remained an integral part of the situation, but the concept of the integral part of the situation, but the concept of probability allowed the nature and extent of this uncertainty to be specified with rigor. Now, second introduction. In QM, probability is an integral part of the situation, as concerning events that have to happen. But because one has to deal with physical events or physical conceived events, and has to take into account the whole geometry underlying this physics. we might think in this frame of a twister. It's a concept invented by Roger Penrose. A twister as representing a light ray in ordinary spacetime M. One can regard, Penrose says, such a light ray as providing the primitive causal link between a pair of events, that means of spacetime points. But events, and what is very important in this frame, events are themselves to be regarded as secondary constants. This being obtained for their role as intersection of light rays. Now, ordinary space-time notions are not initially among the ingredients of twistor theory, but are to be constructed from them. Penrose says, these have good deal in common with the underlying philosophy behind my original, this was the old works by Penrose, original spin networks, where spatial notions are to be constructed from the spin network, rather than the spin network being thought of as inhabiting, previously I think, spatial geometry. To go behind space-time notions. Why? If you manage to adopt a viewpoint on the space-time, your concept of probability and of uncertainty will be totally or relatively different. No. Space-time is taken to be a secondary construction from the more primitive notion twistor. Twistor theory does not directly lead to any notion of discrete space-time. Its departure from real number continuity is in the opposite direction, for it calls upon the magic, Penrose says, magic of complex number as a principle guiding for physics. My goal in this talk will be to show the quantum conception allows to shed light on the ontology of the probability and maybe on uncertainty. Now, a little about quantum mechanics. Are the dynamical variables real things? Are the states real? Or should we say that we have achieved reality only when we have arrived at the seemingly classical quantities that arise as eigenvalues of the dynamical variables? Now, the essential problem in this presentation and for Penrose is the question of the reality of the physical entity. And if we are believed that any one thing in the quantum formalism is actually real for a quantum system, then I think that it has to be the wave function or the state vector that describe quantum reality. Penrose says most of quantum physicists are distinctly uncomfortable about addressing the issue of reality. We need a notion of physical reality, even if only a provisional or approximate one. For without it, our objective universe simply evaporates before the contemplative gaze, Penrose says. Now, a little more technical notion, but that is not very important. That is in the spirit of in the quantum mechanics. We must look more carefully into the nature of wave function and their physical interpretation. Let's examine this equation. Psi is exponential IP, exponent P over H bar. It is in no way localized like in an ordinary particle. It is spread out evenly over the whole of the units. A little commentary about this question. When we want to understand what is the reality for quantum mechanics, we have to change our way to think. For example, we have to change the question of locality, the question of globally and locally, the question of coordinates, and so. And when we change all this frame of thought, we change also evidently the concept of probability, because the concept of probability has to deal with events. Events is with the time, and when you have another thought about time, about space, and so you have another concept of probability. No, for example, what has happened to our ordinary picture of a particle as something localized at a single point? When we say we can still get away with having a very well-defined man to F if we pass to somewhat similar states referred to as wave packets. They are given by wave function. No. 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 After. No. Yes. There is a theorem underlying what is called Heisenberg uncertainty principle. There is an absolute limit to how small its frame can be in relation to how closely, almost as a momentum state it is. Now, a wave function is a complex value wave, and its wavy character is not necessary to be seen as an oscillation in its magnitude or intensity. In the case of a momentum state, it is a wave function's argument taken as measured around a circle, that is this expression, taken on the unit itself in the complex plane, that has heavy character. In quantum theory, we tend to refer to the argument of the value of the wave function as its phase. No, it's a very no. It is a very important ingredient in this thought, in the frame thought of thought. You have the first ingredient, complex number. You have the first ingredient, change with space-time theory, change with probability, and I want to give you some idea about what complex number is very important in this case. A complex number is number in the plane can be described by using the standard Cartesian coordinate x or I for a point in the plane, but one could alternatively use polar coordinates in theta. Now, the positive real number measures the distance from the origin, and the angle theta measures the angle that the line from the origin to the point z makes with the real axis measured in anti-clockwise direction. In this complex number, you have here the argument, and you have here theta, and in this way, you have another way to represent a geometrical entity. And what is very important, in this case, you have together the linear progress and the circular progress. And the mix between linear and circular is a new way to see the geometrical entity. And it's very important also that in this case you have not locality. It's all these entities are globally defined. All the features of this entity are in the whole plane. Encore un peu plus loin. Non, plus bas. No, I am referring to the Penrose figures and in the end of my talk. We repeat this. He plotted the direction of the wave function at an angle sloping up to the right, x-axis of the picture, and taking a plane perpendicular to the direction to represent the complex plane. And to have this phenomenon in the complex plane, the picture plots psi equal U plus IV. You have here the plane, complex, and wave function. Now I will represent for you the new ways to think. Not only obviously it's important to understand what this consists of, but very important is ingredient, that the mix of circular and linear, the complex plane, and the wave function. Now, the x direction corresponds to some actual direction in ordinary space, but the u and v direction are not ordinary spatial direction. They represent the complex plane of possible value of the wave function. The wave function is a cos q, which is right-handed for positive momentum in the spatial direction represented by your picture's x direction. Screwiness ties off in both directions, Penrose says, and the wave function becomes very small outside a certain interval. We will need, but it is more complicated, 2 extra dimensions, 5 in all, in order to fit in the complex plane as well as the spatial dimension. Now, we should have to try to imagine that it is going on all 3 dimensions. It is easier in the case of the momentum state if we just think of the plane of constant phase, parallel planes perpendicular to the direction of the momentum, where the spacing between each plane on the next is dp h bar over p. P is the magnitude of the spatial 3 momentum. Example, picture of a wave function encountering a crystal. In the case, non, on peut aller plus loin. Non, encore, oui, c'est déjà fait, plus loin. No. For example, an electron's wave function approaching the screen in the 2-slide experiment may be regarded as a superposition of 2 of the plane waves mutually tilted. Where the phases agree along the broken line, for example, in the case, the 2 reinforce each other, giving rise to the greatest probability of arrival at the screen. Halfway between maxima, the phases are opposite, and the wave cell, in this case, the waves is cancelled, and the probability is 0. Now, this is the important idea of QM and maybe of the general science, or the general concept of science in this case. We have to think of the entire wave as describing or being just a single particle. As thought it does, in a definite sense, determine the probability that a spot will occur at the various places on the screen, probability for just one particle. No, we should not think of the wave function in a local way, as independently providing a probability of spot formation at each separate place on the screen. We must think of wave function and on entire thing. The ontology is very different in this case, and will be different for the case of the probability concept. If it causes a spot to appear at one place, then it has done its job. And this apparent act of creation forbids it from causing a spot to appear somewhere else as well. Now, we have you have great difference between classical waves and wave function. And we have great difference between classical probability and the quantum probability, and classical geometry and twistor geometry. Different part of the wave cannot be thought of as a local disturbance of each carrying on independently of what is happening in a remote region. The entity is completely opposite. At different level, this conceptual holism is linked with a deep understanding of what the complex reality, complex number, consists of. Complex analytic function, holomorphic function, and twistor reality operates with the holistic and the global conception. Now, what the function psi is supposed to be telling about the particle's position, psi, and essentially squared modulus psi squared, is to be interpreted as a probability distribution, giving the likelihood of a position measurement finding the particle at the various possible location. Wherever the wave function is largest in absolute value, the particle is most likely to be found. If zero, the particle is not to be found. No, it's, can... no.
Okay.
No, these are subtleties on quantum mechanics. The requirement rules out the momentum state wave function in this form, because you must have the absolute value, the norm of psi to the squared equal 1 over the whole infinite space, the integral being equal to the total volume of space diverged. No, it's subtleties. No, we have to make the normalization of this function, and if it does. A wave function will be, in general, normalizable in the integral defining this norm converge. No, this is a technical this mathematically structured concept of probability modifies deeply the concept of probability. I am going to start very briefly to describe this concept. If psi is multiplied by a non-zero constant complex number, then it represents the same physical situation. To regard psi and exponential I psi as being physically equivalent, where theta is a real constant, it is standard. Multiplying the wave function by a constant phase makes no difference to the physical state. It does not affect this expression, because when you have in the square, this equal 1. In a certain sense, the complex number is entangled in mathematical operation in such a way that it makes possible wider mathematical cogeometry structures, where probability is coming from. The wave situation, the wave function is called probability wave, but psi x itself is complex, and so certainty cannot be a probability. The part of psi factor is an ingredient of the Schrödinger equation. There is no information in norm psi telling us even the situation of motion. It is the phase alone that gives this wave its wave-like character emphasized. Wave function cannot be just a wave of probability. The question here is that the complex reality, the complex geometrical reality is very deeply linked with the complex of probability, but after we take the absolute value of this complex number. Now, if we want to represent a quantum state as linear combination of momentum state, now the coefficients as different complex numbers, which we take to be 2p to minus 3 over 2 times the quantity bar on the bar psi. No, we are to this formula, and there is very precise symmetry that is the position as the momentum variables, momentum wave function in terms of the position eigen status. Here we have the inverse Fourier transform, so also technical presentation necessary. Wave packet can be described just as well in the momentum space representation as in the position representation. It is very meaningful for our presentation. One can introduce a precise notion of the spread, of the lack of localization, in either the position description or the momentum description. Let us denote the spread measure respectively by delta x and delta p. Heisenberg's uncertainty relation tells us that the products of the spreads cannot be smaller than the order of the constant of constants Planck, and to have this very famous expression. Now, this remark is not in the extreme case of a pure momentum case, the speed of the momentum is 0, so delta p is 0, from the Heisenberg relation. Delta x will be infinite. A measurement of particles' momentum will put it into a momentum state corresponding to some classical value p, and the same will be obtained for any subsequent measurement of the momentum. If the state were instead subjective to a consequent position measurement following an initial measurement, the result will be completely uncertain, and any one result for the position will be as likely as any other. What the uncertainty consists of? The measurement makes the state of a delta function in position. In momentum space, this state is a plane wave spread out uniformly in all possible values for momentum. A subsequent momentum measurement will then be completely uncertain. Now, passing from the Schrödinger's picture to Heisenberg picture, I shouldn't describe the details for this formalism that is yet very significant. Schrödinger evolution is unitary. There is a linear action of the Schrödinger evolution in the Hilbert space H. In the Heisenberg pictures, the state of the system is considered to be constant in time, the time evolution being taken up by the dynamical variable instant. The Heisenberg picture is just a matter of redefining our symbols. It is the same thing. Historically, Heisenberg was the first producing his sham in July 25, and Schrödinger put forward his proposal half a year later, in January 26, realizing the equivalence between the two schemes, and it was Max Born who first recognized the probability interpretation for the squared modulus psi squared of Schrödinger's wave function in June 26. Now, some measure quality of a quantum system will be represented by a certain kind of operator Q, CLE, and observable, and this operator could be applied to the quantum states. The dynamical variables, such position or momentum, will be examples of observables. The theory demands that an observer Q be represented as a linear operator, so that its action on the space H will be to effect a linear transformation of H. I recall, this is a complex vector space processing and scalar product operation whose value is a complex number which satisfies algebraic properties. Linearity and conjugation. No, it's not very important. But no. The state psi has a definite value for the observer Q if psi is an eigenstate of Q, and the corresponding eigenvalue small q will be that definite value. An essential requirement for an observer is that its eigenvectors corresponding to distinct eigenvalues are orthogonal to one another. Penrose and other physicists explain that it's happy for the result of measurement to be complex, while insisting on the standard requirements of orthogonality between the alternative states that can result from a measurement. Now, this is a linear operator to be normal. It is a definition. Now, according to the rules of QM, the result of a measurement corresponding to some operator Q will always be one of its eigenstates. It is a jumping of the quantum to called quantum state that occurs with air process if in the Penrose terminology of concept and conceptual framework, Schrödinger evolution is denoted by U and state reduction by air. We assign probability to different alternative eigenstates of the observable Q when it is presented with some state denoted on the bracket and that is being observed. The quantum mechanical probability depends only upon the quantum states before and after measurement, and not upon any other after of the observable Q. The rule is that the probability of the state jumping from psi to phi is Q is given by this expression. Alors, vas-y. Encore. Come back to probabilities. Maybe is the most important. Classical probability is based on Boolean algebra, and quantum probability on auto algebra. But auto algebra contains Boolean as substructure. We get a new kind of probabilities and explain it the context in which a new concept emerges. This is an answer to the class of phenomenon the QM treats. The main feature, for example, Michel Pitpol says on other philosopher of quantum mechanics, the main feature of this phenomenon is expressed in the most prevalent of the quantum mechanical point of view, that of the environmental decoherence. In any measuring process, the quantum system under consideration cannot be taken in isolation from its surroundings. When a measurement is performed, each different outcome is entangled with a different state of the environment. Now, the environment will consist of a great many particles effectively in random motion, and the complex details of their location and motion must be taken to be totally unobservable in practical. When some over the unknown environment states to obtain a mathematical object known, for example, as density matrix. Another point sample is known as the consistent history approach due to Griffiths, Holmes, Gell-Mann-Hartel. The consistent history schemes provide a generalization of the standard framework of A. No. It is governed by the Schrödinger evolution determined by H. If, according Penrose, R is a quantum state reduction which takes place when a measurement is performed, in the world case, it seems that there is only the Schrödinger evolution, not the reduction process. Consistent history schemes is a manner to describe these processes, incorporates reduction type procedure into its evolution. In order to make emerging a classical world that will perceive some refined history are singled out, consistent if a certain condition is satisfied, expresses the fact that the probabilities calculated according to the quantum rule satisfy the classical rules of probability. Remarkable fact is that we can combine here classical and quantum probability. It is the case in von Neumann works, where we combine together into one expression what would appear to be two distinct notions of probability. It is very interesting that we need to combine two notions of probability. The main reason for that is that quantum probabilities are probabilities embedded in the environment. A deep work of the concept of probability was realized by Gleason. The concept of probability as seen is thus related to the concept of classical probability, Boolean algebra and Kolmogorov axiomatic, and together to the conceptual context of the QM. The latter point of view shed light on the former, in the same manner as QM shed light on classical physics. I would like to emphasize very briefly the difference between function in classical probability and function from state vectors by applying quantum rules. Classical probability function associates with every event a number bounded by 0 and 1. This event is defined by Kolmogorov as subset of elementary events. This set of subsets is given a Boolean algebra structure. In opposite quantum probability function, because of the Hilbert space property, and are not defined on a Boolean algebra. This algebra is so-called, for example, ortho algebra that contain the Boolean one as substructure. And correlatively classical probability functions are generalized by quantum probability function. For this reason, the QM consists itself as a physical theory of a new extended probability theory. Now, for example, Varadarajan, in his quantum books on quantum geometry, we take the point of view that quantum mechanical systems are those whose logic forms sort of projective geometry and which are consequently not distributive lattices. With such a point of view, it is possible to understand the role played by simultaneously observable quantity, the uncertainty relation, and complementary principle. No, just you know that it is very important to have not distributive lattice. That means, for example, for the color theory, you have not distributive, in not distributive lattice, you can interpret the complementary principle in the case of quantum theory. Not this. For example, it is very important in this case, and you have the theorem, embedding theorem, that in the classical case you can embed the classical logic in some topological space with separated and so properties. In this case, when you want to embed this logical structure in space, the topology is not separate. And the topology is not. And is zero. And you can interpret, and so topologically, from a topological point of view, what it means to be not separated. For example, for the theory of colors, for the theory of perception, and so on. It might be seen a bit surprising that the basic assumption on a quantum system is that its logic is not a distributive lattice. Von Neumann, Heisenberg, for example, says. The point is that only experimentally verifiable statements are to be regarded as member of the logic of the system. As you know, we can verify regarding position or momentum statements about one of them, but not those which involve both of them. The statement regarding motion and or momentum form two Boolean sub-algebra, and there is in general no Boolean algebra which contain both of these Boolean sub-algebras. For this reason, we are using orthocomplementation lattices, which comes from Hilbert space structure. The failure to conjoin different contexts, namely different Boolean structure and many probabilities, implies that one try to articulate these concepts together by means of some extra meta-conceptual logic, therefore quantum non-descriptive logic by von Neumann and Birkhoff. But it's and there is more. I come back to the twister theory. First, it should be possible to give an axiomatic presentation of the property of non-locality. This property is expressed by the complex number, as you know, and the holomorphic function. I cannot realize this work here, but it's possible. The very beautiful cohomology theory developed in the notion of non-locality by means of the sheaf theory. The non-local aspect of twister theory is intimately bound up with the most important of its underlying motivation, namely, Penrose says, to exploit the magic of the complex number in a belief that nature herself might well be dependent upon such thing that means complex number at a deep level. Twister theory, and it is the end, finds a remarkable and unexpected deep relation to general relativity in providing perspective of quantum field theory, particle physics, and places possible nonlinear generalization of quantum mechanics. Whereas in the normal space, time P2, a light ray Z is a locus and an event R is a point, in the theory of Penrose, there is a reversal of this in twister. The instance, the light ray is described as a point Z, and an event is described as a locus R. And this way, the twister perspective led us to a very different view of quantized space-time. The conventional point of view is that the procedure of quantum theory are to be applied to the metric tensor, this being thought as tensor field. One says that the quantized metric will exhibit aspect on fuzziness owing to the Heisenberg uncertainty. The image of some kind of for the space which possesses a fuzzy metric, so that the neurons and the notion of causality becomes subject to quantum uncertainty. Now, it's the last. Normal, you have this normal, light ray and event. It is a point, it is a line. In the frame by Penrose is a reversal. This light line is a point. And this is a point is a sphere. And by means of this representation, you can give a very fuzzy representation of this intersection. Intersection is no more intersection. And no, the appropriate quantization procedure, whatever they may be, must be applied within Richter square rather than the space-time. Whereas null becomes fuzzy, in a twister-based approach, it is now the light ray that are left intact, whereas events becomes fuzzy. And while the event becomes fuzzy, the probability becomes fuzzy, and becomes fuzzy to squares. And inside twister theory and natural actual scheme of things, which must internally unify space-time structure within the procedure of QL. No. This is the most important thing in my talk is here. that means that the point that in the normal representation, the point and gives the probability of this point becomes fuzzy in this representation. And then you have the fuzzy, and you have a new way of thought this even quantum probability. Now, thank you for